What if the story of how the universe began, the one we've all been taught, is wrong? For almost a century, the Big Bang Theory has explained how everything started, from a tiny, unimaginably hot point that expanded into the vast universe we see today. But now, scientists have uncovered a serious flaw in this theory, one they can no longer ignore. New discoveries and sharper observations are revealing cracks in the Big Bang model, forcing experts to question if we truly understand how the universe was born. This controversial error could rewrite the story of creation itself. Historical development of the Big Bang Theory. The journey to our modern understanding of the Big Bang began long before the term Big Bang was ever coined. In the early 20th century, astronomers observed that the galaxies were not static but moving away from one another. Edwin Hubble's groundbreaking discovery in the 1920s, that distant galaxies are receding from us at speeds proportional to their distance, laid the empirical foundation for a dynamic, expanding universe. This observation challenged the long-held belief in a static cosmos, a view that had dominated scientific thought since Newton's time. In response to these observations, Belgian priest and astronomer Georges Lemaitre proposed what he called the primeval atom theory. Lemaitre suggested that the universe originated from a single, incredibly dense point, a hypothesis that was initially met with skepticism by many in the scientific community. Despite the controversy, his ideas gained traction as more evidence accumulated. Over the following decades, the concept evolved as scientists began to reconcile these observations with theoretical frameworks, notably Einstein's general theory of relativity, which predicted that space and time are interwoven and dynamic. The development of the Big Bang theory was further bolstered in the 1940s and 1950s by the work of scientists such as George Gamow, Ralph Alpher, and Robert Herman. They applied nuclear physics to cosmology, developing the theory of Big Bang nucleosynthesis, the process by which the light elements, primarily hydrogen and helium, were formed in the early universe. Their predictions regarding the abundances of these elements provided a crucial test for the theory, setting it apart from competing models such as the steady-state theory. A pivotal moment in the historical development of the Big Bang model came with the accidental discovery of the cosmic microwave background radiation, CMB, in 1965 by Arno Penzias and Robert Wilson. This faint, pervasive glow, interpreted as the relic radiation from the hot, dense early universe, served as compelling evidence in favor of the Big Bang, fundamentally altering our understanding of cosmic origins. The discovery of the CMB provided a snapshot of the universe roughly 380,000 years after its inception, when it had cooled enough for protons and electrons to combine into neutral atoms and light to travel freely. Since then, advancements in both observational astronomy and theoretical physics have continually refined our picture of the Big Bang. Modern telescopes, particle accelerators, and sophisticated computer simulations have all contributed to a more nuanced understanding of the universe's explosive beginnings. Key observational evidence for the Big Bang. The Big Bang theory is based on a lot of strong proof from observations that have changed the way we think about the world over time. The study of star redshifts led to one of the first and strongest pieces of proof. In the 1920s, Edwin Hubble noticed that the light that galaxies far away give off is moved toward longer, redder colors. This redshift means that galaxies are moving away from us, and the speed at which they are moving away is related to how far away they are. This event, which is now called Hubble's law, not only proves that the universe is expanding, but it also supports the idea that it was much smaller, denser, and hotter in the past. Complementing the redshift data is the discovery of the cosmic microwave background, CMB, radiation. In 1965, Arno Penzias and Robert Wilson detected a faint, uniform glow in the microwave region of the electromagnetic spectrum. Initially regarded as an annoying noise, this pervasive radiation was soon recognized as the remnant heat from the early universe, a snapshot of the cosmos about 380,000 years after the Big Bang. The CMB provides a direct link to the past, preserving information about the primordial conditions of the universe. Its near uniform temperature of approximately 2.7 Kelvin, punctuated by minute fluctuations, has been mapped in exquisite detail by satellites such as COBE, WMAP, and Planck. These temperature variations, or anisotropies, are believed to be the seeds of all subsequent structure in the universe, influencing the formation of galaxies and clusters over billions of years. Along with redshift and the CMB, the measured abundances of light elements are also strong proof of the Big Bang. It has been very helpful for understanding the relative amounts of hydrogen, helium, lithium, and deuterium in the universe to use predictions from Big Bang Nucleosynthesis, BBN. Based on measurements, about 75% of the baryonic mass is hydrogen and about 25% is helium. The rest is made up of stronger elements. These numbers are very close to what the theory says they should be, which is a very important test for the model. But differences in how much lithium there is have led to ongoing arguments and study, pushing scientists to improve the standard model of cosmology. Seeing supernovae from a long way away has also helped us learn more about how the universe is expanding. Astonishingly accurate distances can be found between galaxies that are very far away by using Type Ia supernovae as standard candles. These measurements have shown that the universe is not only expanding, but it is also growing faster. This finding led to the addition of dark energy to models of the universe. Dark energy is still one of the most mysterious things in the universe, but its effects can be seen in how it changes the way galaxies move and how big structures change over time. Large-scale surveys of the distribution of galaxies and clusters have provided a comprehensive picture of the cosmic web, the vast network of matter that spans the universe. These surveys show that galaxies are not randomly scattered, but instead are organized into filaments, walls, and voids. This structure is consistent with predictions from the Big Bang model when combined with the effects of cosmic inflation, a rapid expansion that smoothed out the early universe while leaving behind small fluctuations that later grew into the complex cosmic structures we observe today. The cosmic microwave background, a window to the past. The cosmic microwave background, CMB, changed the way we think about the early universe by giving us a clear view of a time when the universe was a hot, dense plasma. As the universe grew and cooled over the next 380,000 years, free electrons and protons joined together to make neutral hydrogen. This is called recombination. Photons were freed from matter at this key shift and could now easily move through space, leaving behind a glow that we now call the CMB. This old radiation is like the glow left over from the Big Bang. It's like a time capsule that holds the conditions of the early universe. Measured today at a nearly uniform temperature of about 2.7 Kelvin, the CMB is not perfectly smooth. It contains tiny fluctuations in temperature at the level of 1 part in 100,000. These minute anisotropies are critically important because they represent the primordial density variations that later grew into the large-scale structures, galaxies, clusters, and superclusters that we observe in the universe today. By mapping these variations in exquisite detail, missions like COBE, WMAP, and Planck have enabled cosmologists to extract a wealth of information about the universe's composition, geometry, and rate of expansion. The significance of the CMB extends beyond merely confirming the universe's hot, dense beginnings. Its detailed measurements allow scientists to test fundamental cosmological parameters with remarkable precision. For example, the pattern of temperature fluctuations provides insight into the proportions of ordinary matter, and dark energy present in the universe. These parameters are crucial for understanding the overall evolution of the cosmos. The angular scale of the anisotropies, along with their statistical distribution, supports the notion of a flat universe, as predicted by the standard cosmological model, and hints at the processes that occurred during cosmic inflation, a rapid expansion that smoothed out the early universe while seeding it with the slight irregularities that later evolved into galaxies. In addition, the polarization of the CMB adds another layer of knowledge. Researchers can look into the effects of gravitational waves from the early universe by looking at the polarized patterns left on the CMB. This could lead to proof of inflationary processes. Finding these primordial gravitational waves would not only help us learn more about the early universe, but it would also help bring together the ideas of general relativity and quantum mechanics. This part of CMB study is on the cutting edge of cosmology. The uniformity of the CMB is itself a remarkable feature. Despite the immense scale of the universe, the CMB appears almost the same in every direction, reinforcing the cosmological principle that the universe is homogeneous and isotopic on large scales. This near-perfect uniformity raises important questions about how different regions of the early universe could have reached thermal equilibrium so quickly, a puzzle that inflationary theory seeks to address by positing that a brief exponential expansion stretched out any initial irregularities, resulting in the smooth cosmic background we observe today. Fundamentals of Big Bang nucleosynthesis. Big Bang nucleosynthesis, BBN, is the process that forged the light elements in the first few minutes after the universe began its expansion. As the universe cooled from its initial hot, dense state, conditions became just right for nuclear reactions to occur, enabling protons and neutrons to combine and form the first nuclei. This epoch, which lasted only a few minutes, set the stage for the chemical evolution of the cosmos, determining the primordial abundances of elements such as hydrogen, helium, and small amounts of lithium and deuterium. The cosmos began as a very hot plasma, with temperatures so high that atomic nuclei could not exist. Instead, free protons, neutrons, electrons, and photons were constantly interacting. As the cosmos expanded, it cooled, and when the temperature dropped to around 10 billion Kelvin, nuclear fusion events could commence. During this brief moment, protons and neutrons collided with enough energy to overcome their repulsive interactions, allowing them to bind together and form the first light nuclei. The dominant reaction during BBN was the formation of deuterium, a heavy isotope of hydrogen, by the combination of a proton and a neutron. Once deuterium was produced, it served as a stepping stone for the synthesis of heavier elements. Through a series of nuclear reactions, deuterium fused to form helium-3 and eventually helium-4. The vast majority of neutrons ended up locked into helium-4 nuclei, resulting in a universe that was approximately 25% helium by mass. A smaller fraction of these neutrons participated in reactions that produced trace amounts of lithium-7 and deuterium. The delicate balance of nuclear reactions during BBN was significantly dependent on the pace of expansion of the cosmos. If the cosmos had expanded too rapidly, there would not have been enough time for nuclear reactions to occur, and the primordial abundances would have been very different. A slower growth, on the other hand, would have enabled more reactions to occur, causing the elemental balance to shift. The exact timing of these reactions demonstrates the Big Bang model's amazing success, since projected hydrogen and helium abundances nearly match observed values in old stars and interstellar gas clouds. The ratio of neutrons to protons at the moment nuclear reactions started determines one of the main characteristics of Big Bang nucleosynthesis. The interaction of the slow cooling of the early cosmos with the weak nuclear force shapes this ratio. Protons and neutrons were in thermal balance at first, but as the temperature decreased, the rate of neutron decay started to surpass that of conversion between neutrons and protons. This resulted in a minor shortfall of neutrons relative to protons, which eventually affected the synthesis of helium and other light elements. Beyond helium, the synthesis of deuterium and lithium serves as a sensitive probe of the conditions in the early universe. Deuterium, for example, is easily destroyed in stellar interiors, so its primordial abundance remains largely unaltered in regions where star formation has not processed much gas. Observations of deuterium in distant, pristine clouds provide one of the most accurate tests of BBN predictions. Similarly, the amount of lithium produced during BBN, though a minor component compared to hydrogen and helium, has become a focal point for testing our understanding of early universe physics, especially given the persistent discrepancy between predicted and observed lithium abundances, which continues to challenge theorists. The capacity of Big Bang nucleosynthesis to link cosmological data with nuclear physics will define its success. Well-known nuclear reaction rates form the basis of BBN's predictions. They have been verified by astronomical observations and laboratory tests. For most light elements, the congruence between measured abundances and theoretical expectations is among the strongest lines of evidence supporting the Big Bang concept. BBN also gives us a unique look into what the world was like in the beginning. Cosmologists can figure out important things about the early universe, like the ratio of baryons to photons and the rate of expansion, by comparing the amounts of elements that have been found to what has been predicted by nucleosynthesis models. These new ideas not only help us understand more about how the world came to be, but they also put limits on new physics that could change the usual picture. Formation of light elements, hydrogen and helium. As the cosmos cooled below approximately 10 billion Kelvin, the free protons and neutrons, previously in a state of rapid interchange, found themselves in a new environment where nuclear fusion could take hold. This cooling phase created the ideal conditions for the synthesis of light elements, most notably hydrogen and helium, which now dominate the chemical composition of the observable universe. Deuterium, a heavy form of hydrogen, was the first thing to form in the process. Neutrons and protons met and fused to make deuterium nuclei during the short time when the universe's temperature and density were just right. Deuterium was an important first step. Once it was created, it could fuse with other atoms to make helium-3 and then helium-4, which is the most stable and common form of helium. At that time, protons were more common than neutrons, so almost all the neutrons that were available were put into helium-4 nuclei. This made the universe about 25% helium by mass and 75% hydrogen by mass. These numbers are not made up. They are a direct result of the neutron-to-proton ratio that became stable as the universe grew and cooled, as well as the fast decay of free neutrons before they could join fusion processes. Helium-4, with its exceptionally strong nuclear binding energy, emerged as the end product of these fusion chains. The efficiency of helium production was such that nearly all neutrons available were quickly captured into helium nuclei. This rapid synthesis ensured that helium became a dominant component, even though its formation window was incredibly brief, lasting only a few minutes in the early universe. In contrast, the formation of heavier elements was largely suppressed during this era due to the insufficient density and the rapid drop in temperature, which prevented further fusion reactions from occurring. Hydrogen, which remains the most abundant element in the universe, was the starting point for all subsequent chemical evolution. Not only did the overwhelming majority of hydrogen remain unprocessed into helium or other elements, but it also provided the primary fuel for the first generation of stars. These stars, forming millions of years after the Big Bang, would later act as cosmic forges, synthesizing heavier elements through nuclear fusion during their life cycles and in supernova explosions. The primordial hydrogen and helium, created during Big Bang nucleosynthesis, thus set the initial conditions for all later structure formation and chemical evolution in the universe. Several astronomical studies have proven that hydrogen and helium are more common than Big Bang nucleosynthesis said they would be. Spectroscopic studies of old pure gas clouds, which are often found near the edges of galaxies, show that their makeup are very similar to what scientists think they should be. The numbers that have been seen to be stable across different parts of the universe strongly support the standard model of cosmology and show that nucleosynthesis happened quickly and efficiently in the early universe. Hydrogen and helium have been well accounted for, but the process that made them also set the stage for the lithium problem, which is one of the most puzzling problems in astronomy. in the same high-temperature setting that made it easier for protons and neutrons to fuse together to make deuterium, some processes also made very small amounts of lithium isotopes. Lithium was thought to be less common than hydrogen and helium, but there are still differences between theory models and actual data. This suggests that our knowledge of the early universe may still be lacking. The creation of light elements was more than just a chemistry process. It was a key stage that changed the course of the universe's history. The successful mixing of hydrogen and helium made it possible for stars to form, galaxies to change over time, and finally for life to start. The first few minutes after the Big Bang saw nuclear reactions that set off a chain of events that would eventually lead to the complex structures we see in space today. Introducing the lithium problem. Even though the Big Bang model was very good at predicting how much hydrogen and helium there would be, the lithium problem is still a mystery that makes it hard to understand how the universe got started. Standard Big Bang nucleosynthesis says that in the first few minutes after the Big Bang, only very small amounts of lithium should have been made. But when scientists check the levels of lithium, especially the element lithium-7, in old, almost perfect stars and gas clouds, they find that they are about 3 times lower than what the theory says they should be. This difference has not only caused a heated argument between cosmologists and nuclear scientists, but it has also made us wonder if our current models of how the universe came to be are complete. The origins of the lithium problem can be traced back to the conditions prevailing in the first few minutes after the Big Bang. During this epoch, as the universe cooled from its initial extremely high temperatures, nuclear reactions commenced, and protons and neutrons fused to form deuterium, helium, and small quantities of lithium. The reaction rates and the neutron-to-proton ratio at that time were thought to be well understood, and the standard model of nucleosynthesis has been remarkably successful in explaining the observed abundances of most light elements. However, lithium-7 has stubbornly defied these predictions. While the predicted yield of lithium-7 is based on well-established nuclear reaction cross-sections and measured baryon-to-photon ratios from the cosmic microwave background, the consistently lower observed lithium levels in population 2 stars suggest that either our understanding of these nuclear processes is incomplete, or that additional astrophysical processes are at work after the primordial synthesis. An avenue of investigation suggests that the lithium in the atmospheres of ancient stars could be being depleted by some process. Over the course of billions of years, lithium might be transported from the surface to deeper strata, where it is destroyed by greater temperatures by processes such as atomic diffusion, mixing, and convective movements. Although stellar models that include these processes have been created, the measured lithium abundance is still lower than what is predicted theoretically, and this is true even after taking into consideration the possibility of depletion. Researchers have begun to wonder if nucleosynthesis is being affected by non-standard physics as a result of this. Another possibility is that the nuclear reactions themselves might have been changed by physics not included in the standard model when they happened in the early world. Some ideas say that changes in fundamental constants, the appearance of extra neutrino species, or interactions involving made-up particles could affect how fast the reactions that create and destroy lithium happen. To give an example, even small changes in the nucleosynthesis epoch could have a big effect on the end supply of lithium. This is because the nuclear forces and neutron decay rates could be affected. These changes would have an effect on lithium, but they could also have an impact on the creation of other elements. However, it is very hard to make sense of these changes when measuring the amounts of hydrogen and helium very accurately. The lithium problem is further complicated by the dual nature of lithium isotopes observed in the universe. While lithium-7 is the more abundant isotope produced during Big Bang nucleosynthesis, lithium-6 is expected to be present in only very minute amounts, on the order of a few parts per 100,000. Yet, some observations indicate that lithium-6 might be more prevalent than our models predict, adding another layer of complexity. The unexpectedly high ratio of lithium-6 to lithium-7 has forced scientists to re-examine the nuclear reactions and potential astrophysical sites for lithium production and destruction, ranging from cosmic ray spallation to stellar flares. The fact that the lithium problem has been around for a long time has big effects on how we think about the early world. If the difference is caused by knowledge gaps in nuclear physics, then fixing the problem could lead to better models of how stars form and evolve and more accurate measures of reaction rates. If the answer lies in new physics, on the other hand, it could point to things that aren't explained by the standard model. It could even point to interactions that were very important in the beginning of the universe but aren't understood much now. Not only does this have big effects on astronomy, but it could also mean that the forces and particles that ruled the first few seconds after the Big Bang need to be rethought. The lithium problem is a very important way to test how stable the Big Bang model is as a whole. The fact that the amounts of hydrogen and helium can be forecast very accurately, but lithium is still a problem, suggests that the processes that control nucleosynthesis may be delicately balanced. If we could figure out this balance better, we might learn more about how the early universe worked, like how growth, cooling, and nuclear processes affected each other. It also shows how important precise readings of space are. Spectroscopic measurements of old stars and gas between stars are still getting better, putting tighter limits on the amounts of different elements. Detailed analysis of lithium-7 and lithium-6 isotopes. A deeper look into the lithium problem reveals that not all lithium is created equal. It exists mainly in two isotopic forms, lithium-7 and lithium-6. Understanding the properties, production mechanisms, and expected ratios of these isotopes is critical in unraveling why our theoretical predictions diverge from observational data. Lithium-7 is predicted to be the dominant isotope formed during Big Bang nucleosynthesis, while lithium-6 is expected to be produced in only minuscule quantities. However, the observations indicate that the abundance of lithium-7 is lower than predicted, and in some cases, the ratio of lithium-6 to lithium-7 appears unexpectedly high, leading to significant scientific debate. During the initial stages of nucleosynthesis, when the universe cooled enough to allow nuclear reactions, the formation of both lithium isotopes was governed by a complex network of reactions. Lithium-7 is predominantly produced through two key pathways. One involves the direct synthesis from helium-3 and helium-4 via reactions such as helium-3, alpha, gamma, beryllium-7, which subsequently decays into lithium-7 by electron capture. Another pathway includes the fusion of tritium with helium-4, although this reaction contributes less significantly. In contrast, lithium-6 formation is even more sensitive to the conditions of the early universe. Its production is thought to occur via the fusion of deuterium with helium-4, a reaction that has a much lower cross-section and is therefore far less efficient. Consequently, standard nucleosynthesis models predict that lithium-6 should be present at levels several orders of magnitude lower than lithium-7. The expected isotopic ratio is one of the most critical outputs of Big Bang nucleosynthesis models. These models, which are based on well-established nuclear physics, typically forecast a lithium-7 to lithium-6 ratio that is extremely high, given the inefficiency of lithium-6 production. However, spectroscopic observations of metal-poor halo stars and ancient gas clouds sometimes indicate a lithium-6 abundance that is disproportionately high relative to lithium-7. Such a discrepancy challenges the robustness of our nucleosynthesis calculations and suggests that either the nuclear reaction rates used in these models are not accurate under the conditions of the early universe, or that additional processes may be altering the lithium isotopic abundances post-nucleosynthesis. One idea to explain the difference is that processes inside stars might be removing lithium-7 more quickly than lithium-6 in the star's upper layers. When old stars have rough convection zones, lithium can be moved from the surface to hotter areas where it is killed by proton capture. If lithium-7 is more easily damaged by these processes than lithium-6, then the amount of lithium-7 on the surface of old stars may have decreased over time. There are some problems with this stellar depletion situation, though. The depletion needs to be carefully controlled so that it reliably lowers lithium-7 without affecting lithium-6 in the same way. Also, many stellar models have trouble reproducing the observed isotopic ratios, even when these processes are taken into account. A further potential is that the nuclear processes that happened in the first few minutes after the Big Bang may have been affected by physics that we don't fully understand yet. For example, if there were small changes in the fundamental constants or unknown particle interactions at that time, they might have affected the speeds of the reactions that made lithium isotopes. The expected amounts of lithium-7 and lithium-6 could change a lot if the strength of the nuclear force or the reaction cross-sections changed even a little. They think that new physics, like the decay of imagined massive particles or changes in the amount of neutrino species, may have had an impact on the final isotopic ratios. Not only would these changes affect lithium, but they might also have effects on the whole structure of nucleosynthesis. Cosmic ray interactions and non-primordial processes might contribute to the lithium isotopic abundances observed today. Over cosmic timescales, cosmic rays can induce spallation reactions in the interstellar medium, creating additional lithium isotopes. While these processes are generally considered secondary and are insufficient to account for the bulk of the lithium present, they might partly explain the higher than expected levels of lithium-6 in some observations. So the task is to find a way for the observations and the expectations from Big Bang nucleosynthesis to fit together. To do this, we need to not only improve our models of nuclear reactions by taking more accurate readings in the lab, but we also need to learn more about stellar physics and chemical development after the Big Bang. Astronomers need to make big steps forward in spectroscopic methods so they can more accurately measure the lithium isotopic ratios. This is necessary to test these theoretical claims. Also, more studies of very metal-poor stars that haven't been changed much since they were formed will give us tighter limits on the amounts of lithium in the early universe. Spectroscopic techniques in cosmology. Scientists can figure out a lot about the makeup, speed, and physical state of celestial objects by decoding the light they give off. This is why spectroscopy has been one of the most useful tools in astronomy for a long time. In astronomy, spectroscopic methods are essential for finding out the redshifts of objects, measuring the abundances of elements, and charting the history of the universe from its earliest days to the present day. In spectroscopy, light is broken up into its individual colors, like how a prism makes a rainbow out of white light. When light from faraway galaxies, stars, or interstellar dust goes through this process, different chemical elements either block or send out certain wavelengths. In the form of spectral lines, narrow bands of light at specific wavelengths, each element leaves a unique mark. Astronomers can figure out what elements are in the material that is releasing or absorbing light, and how common they are by comparing these lines to standards that have been made in the lab. The study of redshifts is one of the most important uses of spectroscopy in astronomy. The bands of light from faraway galaxies get longer as the universe grows. This moves their spectral lines toward the red end of the spectrum. This redshift not only proves that the universe is getting bigger, but it also lets us figure out how far away these things are. Scientists can make a three-dimensional map of the universe by looking at the redshift of spectral lines. This shows how galaxies, clusters, and cosmic gaps are structured on a large scale. The accuracy of spectroscopic redshift readings has helped us prove Hubble's law and get a better idea of how fast the universe is expanding. Spectroscopy also plays a crucial role in the study of the cosmic microwave background, CMB. While the CMB itself is measured primarily in the microwave region, spectroscopic analyses of its slight temperature fluctuations and polarization patterns have provided insights into the physics of the early universe. These subtle variations, observed with instruments aboard satellites like COBE, WMAP, and Planck, allow cosmologists to constrain models of cosmic inflation and the initial density fluctuations that seeded the formation of galaxies and larger structures. In the context of nucleosynthesis, spectroscopy is vital for determining the primordial abundances of light elements, such as hydrogen, helium, deuterium, and lithium. By observing ancient stars and interstellar clouds, particularly those with very low metallicity, that is, minimal heavy elements, researchers can access near-primordial chemical compositions. The spectral lines of these light elements provide direct evidence of the conditions that prevailed during Big Bang nucleosynthesis. For instance, the strengths of the hydrogen and helium lines in the spectra of ancient stars help confirm the predictions of their relative abundances, while the detection of deuterium serves as a sensitive indicator of the density and temperature of the early universe. Modern spectrographs, attached to both ground-based and space telescopes, have dramatically increased the precision with which these measurements can be made. Instruments with high spectral resolution allow scientists to resolve even the narrowest spectral lines, leading to more accurate determinations of element ratios. These advancements have been key in investigating the lithium problem, a notable discrepancy between the predicted and observed abundances of lithium isotopes in the early universe. High-resolution spectroscopy can differentiate between the subtle differences in the wavelengths of lithium-7 and lithium-6 lines, providing critical data that challenge and refine nucleosynthesis models. Spectroscopic methods are also not limited to wavelengths of light. Different observations in the electromagnetic range, like ultraviolet, infrared, and X-rays, give us different kinds of knowledge that work together. For instance, infrared spectroscopy is great for studying parts of the universe that are hidden by dust. It lets scientists see into the deepest parts of galaxies and the early stages of star formation. X-ray spectroscopy, on the other hand, helps us understand high-energy processes better, like those happening near black holes or in the remains of supernovae. This helps us learn more about how the universe changes over time. The integration of spectroscopy with other observational methods, such as photometry and gravitational lensing, has enabled a more comprehensive view of cosmic phenomena. Multi-wavelength campaigns that combine data from different parts of the spectrum help to cross-validate findings and provide a fuller picture of the physical processes at play. This holistic approach is critical in cosmology, where the complexity of the universe often requires multiple lines of evidence to build robust models. Observational data on elemental abundances. Observational data on the amounts of elements are very important for proving that the expectations of Big Bang nucleosynthesis are correct. Scientists have spent decades carefully studying astronomy and have gathered a lot of data that helps them figure out how much of light elements like hydrogen, helium, deuterium, and lithium are in different parts of the universe. These findings, mostly from spectroscopic studies of old stars and gas clouds far away, give us a picture of the chemicals that made up the early universe and are necessary for testing cosmic models. The study of very old, metal-poor stars, which are often found in the galaxy halo, is one of the best ways to find out how common primitive elements are. The chemicals that were around when these stars were born have been kept alive because they formed early in the history of the world. Astronomers can figure out how much of each element is in the atmospheres of stars by looking at the absorption lines in their spectra. For instance, the levels of the hydrogen and helium lines in these stars mostly match what the Big Bang nucleosynthesis predicted. By mass, these stars are about 75% hydrogen and 25% helium. These numbers have been incredibly stable across a wide range of star populations. This supports the standard model of the universe. Investigating the interstellar medium, ISM, in areas seeing little chemical development is another important observational method. Gas clouds in far-off galaxies or on the margins of our own galaxy offer immaculate settings where the initial composition has not been much changed by later star events. Deuterium levels in these clouds frequently show close agreement to theoretical assumptions in spectroscopic observations. Deuterium's abundance serves as a precise gauge of the density and temperature in the early cosmos, as it is readily destroyed in star interiors and very sensitive to the circumstances during nucleosynthesis. One of the most strict tests of the nucleosynthesis hypothesis are high deuterium values from quasar absorption systems. Observations of the cosmic microwave background, CMB, also help to improve our understanding of elemental abundances. Early universe baryonic matter density is encoded in the minute temperature oscillations in the CMB as detected by satellites including COBE, WMAP, and Planck. Cosmologists can deduce the baryon to a photon ratio by examining these variations. This is a crucial factor affecting the expected quantity of light elements. Strong evidence for the Big Bang theory comes from the consistency between the baryon density, calculated from CMB data, and that needed by nucleosynthesis models to generate the observed hydrogen and helium levels. Lithium, on the other hand, is an interesting case. Although measurements of hydrogen, helium, and deuterium fit theoretical expectations, the quantity of lithium found in old stars is much below predicted. Focused on the lithium-7 isotope, detailed spectroscopic investigations have shown a consistent difference, now known as the lithium problem. Some studies showing an apparently high ratio of lithium-6 to lithium-7 in some star populations aggravate this problem. These deviations in lithium readings have sparked intense discussions and re-evaluations of both observational methods and theoretical frameworks. Advances in instrumentation have continually refined our measurements. Modern high-resolution spectrographs attached to both ground-based telescopes and space observatories now enable astronomers to detect even subtle spectral features. This increased precision has allowed for a more detailed mapping of elemental abundances across different cosmic environments, from the dense cores of galaxies to the diffuse outskirts of intergalactic space. Theoretical predictions of elemental abundances. The theoretical framework of Big Bang nucleosynthesis, BBN, is built upon a series of well-established physical principles that predict the production of light elements during the first minutes after the Big Bang. By combining our understanding of nuclear physics with cosmological parameters, such as the baryon-to-photon ratio and the expansion rate of the early universe, cosmologists have developed detailed models that forecast the abundances of hydrogen, helium, deuterium, and lithium. These predictions are based on a network of nuclear reactions occurring under extreme temperatures and densities, which have been refined through decades of experimental and theoretical work. The neutron-to-proton ratio is fundamental to these ideas. It was established in the early cosmos when it cooled from a very hot, dense condition. Protons and neutrons first were in thermal equilibrium and underwent modest interaction into conversion. These interactions started to freeze out as the cosmos grew and the temperature decreased, leaving a residual ratio that greatly affects the ultimate production of helium-4, the most stable and closely linked nucleus among the light elements. Predicted helium-4 mass percentage of around 25%, derived from calculations based on known decay rates of neutrons and the rate of cosmic expansion, fits very nicely with astronomical measurements. In addition to helium, these models predict the synthesis of deuterium, a key stepping stone for the production of heavier nuclei. Since deuterium is easily destroyed in stellar interiors, its abundance in primordial clouds serves as a sensitive indicator of the conditions prevailing during nucleosynthesis. The predicted deuterium abundance is highly dependent on the baryon density of the universe. Higher baryon density results in more deuterium being burned into helium, leading to lower residual deuterium levels. Modern measurements of the cosmic microwave background, CMB, have provided an accurate determination of the baryon-to-photon ratio, thereby enabling precise predictions for deuterium, which have been largely confirmed by spectroscopic observations of distant gas clouds. Lithium, however, poses a unique challenge. The theoretical models predict that lithium-7 should be produced in trace amounts, roughly a few parts per 10 billion, by number relative to hydrogen. These predictions come from two primary reaction pathways, one where helium-3 fuses with helium-4 to form beryllium-7, which then decays into lithium-7, and a less dominant route involving tritium. While the calculated lithium-7 abundance is sensitive to both the nuclear reaction rates and the baryon density, the standard BBN model consistently overpredicts the amount of lithium-7 when compared to observations. Moreover, these models predict that lithium-6 should be produced at levels several orders of magnitude lower than lithium-7. The disparity between these theoretical values and the spectroscopically measured abundances has given rise to what is widely known as the lithium problem, a puzzle that remains unresolved despite rigorous testing of reaction rates and cosmological parameters. The theoretical predictions rely heavily on precise nuclear physics data. Reaction cross-sections, which determine the likelihood of nuclear interactions, have been measured in laboratory settings, and these measurements are incorporated into BBN models. Small uncertainties in these cross-sections can lead to significant variations in the predicted abundances. In recent years, improved experiments and updated reaction networks have reduced some of these uncertainties. Yet the lithium discrepancy persists, suggesting that there might be either unknown astrophysical processes at work or new physics beyond the standard model. The pace of universe expansion during nucleosynthesis is yet another vital factor. The Hubble parameter at that moment controls the rate of temperature decline, which influences the duration accessible for nuclear processes. A rapid expansion would reduce the time available for reactions to take place, therefore changing the ratio of production to destruction of different isotopes. To fairly estimate elemental yields, theoretical models must thus combine the expansion dynamics as given by the Friedmann equations. Furthermore, theoretical research has investigated the potential implications of physics outside the typical BBN framework. To alter the projected abundances, ideas involving decaying relic particles, new neutrino species, or modifications in basic constants have been proposed, notably for lithium. While these expansions are hypothetical, they demonstrate the sensitivity of nucleosynthesis results to underlying physics. Comparing theory and observation, the lithium discrepancy. The lithium discrepancy is one of the most puzzling problems in astronomy. It means that the amounts of lithium expected to have been present in the beginning of time, especially lithium-7, don't match up with the amounts found in old stars and gas between the stars. The standard Big Bang Nucleosynthesis (BBN) model has a lot of luck estimating how much hydrogen, helium, and deuterium there will be. However, it predicts that there will be about 3 times as much lithium-7 as there is. This discrepancy makes us wonder about either the nuclear processes going on in the first few minutes after the Big Bang, or the astronomical processes that may have changed lithium levels over time. According to BBN models, the formation of lithium-7 is primarily driven by nuclear reactions that occur once the universe has cooled sufficiently from its initial extremely hot state. One of the main reaction pathways involves the fusion of helium-3 with helium-4 to form beryllium-7, which later decays into lithium-7 by electron capture. An alternate, less significant path involves reactions with tritium. These reactions are well understood within the framework of nuclear physics, and their rates have been measured in laboratory experiments. When these reaction rates are combined with the baryon to photon ratio, determined with high precision by cosmic microwave background (CMB) observations, the theoretical models yield a lithium-7 abundance that is robust. Yet, when astronomers observe population 2 stars in the galactic halo, which are thought to preserve near-primordial chemical compositions, they consistently measure lithium levels that fall significantly short of these predictions. The gap between theory and observation has prompted scientists to explore a range of potential explanations. One possibility is that the surface layers of these ancient stars have experienced lithium depletion over time. In stellar interiors, various processes such as convection and diffusion could transport lithium from the observable surface to hotter regions where it is destroyed by nuclear reactions. However, while stellar models incorporating such depletion mechanisms can reduce the predicted lithium-7 abundance somewhat, they typically do not account for the full factor of 3 discrepancy observed. This suggests that either the depletion is more efficient than currently modeled, or that additional processes are at play. One more way to look into this is to think that the rates of nuclear reactions might not be as well limited as was first thought. There could be big changes in the expected yields of lithium isotopes, even if the cross-sections of key reactions are only slightly off. Even though studies in the lab have helped us get a better idea of these reaction rates, it is still very hard to exactly recreate the conditions in the early universe on Earth because they were so extreme. It's possible that unknown factors, such as non-standard interactions or changes in fundamental constants during the nucleosynthesis stage, could have slightly sped up or slowed down these reactions, causing theoretical models to overestimate the production of lithium-7. When you look at the isotope ratio of lithium-6 to lithium-7, things get even more complicated. According to standard BBN models, lithium-6 should be made at amounts that are many orders of magnitude lower than lithium-7. However, some data show that lithium-6 is more common than these models predict. This surprising number adds to the mystery. It suggests that there may be other sources of lithium-6, like cosmic ray spallation, or that we need to rethink how we understand the nucleosynthetic roots. Also, the higher generation of lithium-6 might show that there was new physics at the start of the universe, like strange particles or interactions that tipped the balance between the two isotopes. The lithium discrepancy thus stands at the intersection of astrophysics, nuclear physics, and cosmology. Resolving it requires not only refining our understanding of the nuclear processes during the Big Bang, but also a careful re-examination of the astrophysical environments in which these elements are observed today. Some researchers propose that more detailed models of stellar evolution might account for differential lithium depletion, while others advocate for a reassessment of the conditions prevailing during nucleosynthesis itself. Furthermore, high-precision spectroscopy is continuously improving, and future observations of even older and more pristine stars may provide new insights that could bridge the gap between theory and measurement. Besides these common approaches, other theory models have been put forward. Some models suggest that things that aren't explained by the standard model of particle physics, like the decay of heavy relic particles or changes in the features of neutrinos, might be able to change the nuclear reaction network during nucleosynthesis. These models could lead to less lithium-7 being made in the initial state without changing the accurate estimates for hydrogen and helium. But adding this kind of new physics needs to be carefully thought out, because any changes must be in line with a lot of observational data from both astronomy and particle physics. Revising nucleosynthesis models. In the last few decades, the normal model of Big Bang nucleosynthesis, BBN, has been a reliable way to guess how many light elements were in the beginning of the universe. But the constant difference, most notably the fact that too much lithium-7 is being made compared to what is seen, has led experts to look at these models again and make them better. In order to make theory forecasts more consistent with observational data, nucleosynthesis models need to be revised. This means looking at both the nuclear reaction networks and the astrophysical conditions that controlled the early universe again. The speeds of nuclear reactions are one area of study that is very important in the first few minutes after the Big Bang. Lithium-7 is mostly made when helium-3 and helium-4 fuse together to make beryllium-7, which then breaks down into lithium-7. Small differences in these reaction rates, especially the cross-sections for making and breaking down beryllium-7, could cause big differences in how much lithium-7 is thought to be in the universe. Recent studies have tried to get rid of these doubts by taking more accurate readings in conditions that are similar to those in the early universe. Researchers are now adding new experimental data to models of nucleosynthesis to see if these changes could naturally lower the predicted supply of lithium-7 without changing the accuracy of the estimates for hydrogen and helium. Another modification under consideration is the inclusion of additional processes that could influence the effective neutron-to-proton ratio at the onset of nucleosynthesis. The balance between neutrons and protons is a key determinant of the resulting element abundances, especially for helium and lithium. New physics scenarios, such as the decay of massive relic particles or variations in the neutrino sector, have been proposed to subtly shift this ratio. For instance, if there were a slightly higher rate of neutron decay or an additional channel through which neutrons are converted, the resulting abundance of lithium-7 might be reduced. These proposals are attractive because they not only address the lithium problem, but could also offer insights into physics beyond the standard model. Changes to theories of nucleosynthesis also look into the idea of unusual relationships in the early universe. There is some theoretical work that says the reaction pathways and rates could be greatly changed if basic factors, like the strength of the nuclear force or the electromagnetic coupling, changed even slightly during nucleosynthesis. Even though the idea of changing constants is very much a guess, even small changes could have a big effect on the combination of elements. More complex models now include situations where these factors are treated as changing variables. This is done to see if this kind of change could help connect what was predicted and what was observed. A further significant variable is how the rate of growth of the universe was handled during the nucleosynthesis era. The rate at which the universe cooled changes both the amount of time that is available for nuclear processes and the conditions under which different isotopes freeze out. Recent improvements in astronomical data, especially those that deal with the cosmic microwave background, CMB, have made it easier to figure out how the universe began to expand. Researchers are looking again at how the growth of the universe affects the production of elements by changing the parameters that go into BBN models. These parameters include the baryon-to-photon ratio and the effective number of neutrino species. A small change in the rate of growth could cause a different freeze-out time, which could lower the lithium-7 yield while keeping the hydrogen and helium forecasts the same. Some revisions consider the possibility that early stellar processes may have contributed to modifying the primordial lithium abundance before these elements were locked away in long-lived stars. The first generations of stars, known as population 3 stars, might have experienced mixing or other mechanisms that depleted lithium from their outer layers, subsequently altering the measured abundance in ancient stellar atmospheres. Although this does not directly change the nucleosynthesis process itself, it requires that theoretical models incorporate a post-BBN evolutionary phase where lithium destruction could occur. By coupling nucleosynthesis with models of early stellar evolution, researchers are exploring a more integrated approach to explain the discrepancy. Revised nucleosynthesis models also benefit from advancements in computational astrophysics. High-resolution numerical simulations that couple nuclear reaction networks with hydrodynamic models of the early universe provide a more detailed picture of how temperature, density, and expansion rate interact. These simulations allow researchers to explore a wider parameter space and test the sensitivity of elemental yields to small changes in reaction rates or cosmological conditions. Through iterative refinements, the models become increasingly sophisticated, offering potential pathways to resolve the lithium problem. The role of particle physics in the early universe. In the moments right after the Big Bang, the universe was a boiling pot of basic particles. The way it changed was controlled by the way these particles and fundamental forces interacted with each other. We need to know about particle physics to fully grasp how the early universe changed and how the amounts of light elements were set during the Big Bang nucleosynthesis. In this part, we look at the part that particles and their interactions played in the very beginning of the universe. These interactions set the stage for the chemistry and molecular changes that came later. Simple particles like quarks, leptons, and gauge bosons, which made up the cosmic soup, are at the center of all of these processes. In the very early stages of the Big Bang, when energy levels were very high, quarks and gluons moved around easily in a state called the quark-gluon plasma. The strong nuclear force caused these quarks to stick together as the universe grew and cooled. This made protons and neutrons. Hadronization was the first step in nucleosynthesis, which is when these nucleons joined together to make light nuclei like deuterium, helium, and small amounts of lithium. The behavior of neutrinos, nearly massless particles that interact only weakly with other matter, also played a crucial role. Neutrinos maintained thermal equilibrium with other particles in the early universe, influencing the rate of expansion and the freeze-out of various nuclear reactions. Their decoupling from the rest of the cosmic plasma, occurring roughly 1 second after the Big Bang, provided critical timing for when the conditions became favorable for nucleosynthesis to begin. The precise balance between the weak interaction rates and the expansion of the universe dictated the neutron-to-proton ratio, a key parameter that determined the eventual production of helium and other light elements. The role of imaginary particles and reactions that go beyond the standard model of particle physics is another important factor. Some models say that there might be more types of neutrinos or other light particles that could have changed how the early universe worked. The total energy level and the rate of growth would have changed because of these extra particles. This would have changed the conditions in which nucleosynthesis took place. If these factors are changed, it's possible that the expected amounts of light elements, including the hard-to-find lithium isotopes, will change. This could help solve the lithium mystery. In addition to standard particles, phenomena such as CP violation, the asymmetry between matter and antimatter, are critical for understanding why the universe today is dominated by matter. Even a slight imbalance in the early universe could have led to the excess of matter over antimatter, setting the stage for the formation of stars, galaxies, and ultimately life. Particle accelerators on Earth, such as those at CERN, simulate high-energy conditions similar to those of the early universe. These experiments allow physicists to probe the interactions and decay processes that were once prevalent in the primordial plasma, providing valuable insights that feed back into cosmological models. The exact readings of the cosmic microwave background, CMB, also show how particle physics and cosmology work together. The cosmic microwave background, CMB, not only shows the universe as it was during recombination, but it also shows how the physics worked during nucleosynthesis. The measured anisotropies in the CMB put limits on the density of baryons and the number of neutrino species that are actually present. These are important factors that are directly related to how particles interacted in the early universe. Influence of dark matter on element formation. Dark matter is hard to see and locate, but it is very important to the structure of the universe and the processes that control the formation of elements in its early stages. Dark matter is different from normal baryonic matter because it doesn't deal with electromagnetic energy. This means that it doesn't give off, absorb, or reflect light. However, its gravity pull can't be denied. In the early universe, dark matter held together the normal matter that was clumped together. This gravitational pull sped up the collapse of gas clouds, making it possible for the first stars and galaxies to form. It also had a secondary effect on the nuclear processes that happened during the Big Bang nucleosynthesis, BBN. In the first few minutes after the Big Bang, the universe was a hot, dense plasma, where nuclear reactions synthesized light elements such as hydrogen, helium, and trace amounts of lithium. While dark matter did not participate directly in these nuclear reactions, its presence affected the overall dynamics of the universe. The gravitational wells created by concentrations of dark matter could have led to slight variations in density and temperature across different regions of the early universe. These inhomogeneities, although subtle, might have influenced the rate at which nuclear reactions occurred locally, potentially leading to variations in the abundances of light elements. One area of active research is the potential impact of dark matter on the expansion rate of the universe during nucleosynthesis. The overall density of the universe, including both baryonic and dark matter, determines how quickly the cosmos expands and cools. A higher density could cause the universe to expand more slowly, allowing more time for nuclear reactions to take place and possibly altering the final elemental abundances. Conversely, if dark matter were more diffusely distributed, or if its interaction with baryonic matter influenced the expansion rate differently, the cooling rate of the universe could change, affecting the freeze-out times for various reactions. In this way, dark matter indirectly sets the conditions under which nucleosynthesis operates. Also, the way dark matter and regular matter interact could change how the first stars, called population 3 stars, are formed. These stars are thought to have formed in areas where dark matter has a lot of power. When they formed, it was a major turning point in the history of the universe. They started the process of reionizing the universe and introducing heavier elements into the space between stars through supernova blasts. The light elements that were made during BBN were the building blocks for these early stars. As population 3 stars changed over time and finally burst as supernovae, they made and spread heavier elements, which had an effect on the chemical evolution of the universe. How well and when these things happen depend on where the dark matter is located and how it affects gravity. Observational evidence for dark matter comes from a range of astronomical measurements, including the rotation curves of galaxies and gravitational lensing effects observed in galaxy clusters. These observations confirm that dark matter constitutes a significant fraction of the total mass in the universe, which in turn underscores its influence on cosmic evolution. Although dark matter's precise nature remains one of the biggest mysteries in modern physics, its impact on the early universe is unmistakable. Models that incorporate dark matter help to explain not only the formation of large-scale structures, but also provide essential context for understanding the conditions during nucleosynthesis. Role of dark energy in cosmic evolution. The main thing that is speeding up the growth of the universe is dark energy, a mysterious force that makes up about 68% of the universe's overall energy density. Dark energy seems to have an opposing force, pushing galaxies far apart. This is different from dark matter, which pulls things together through gravity. This pressure from the outside affects not only the shape of the universe as a whole, but also the conditions in which early cosmic processes, like nucleosynthesis, took place. In the moments following the Big Bang, the universe was a hot, dense plasma where nuclear reactions forged the light elements. During this epoch, the rate at which the universe expanded played a critical role in determining the outcome of these nuclear reactions. Dark energy contributes to this expansion, setting the pace at which the cosmos cools and allowing or preventing certain reactions from occurring. If the expansion rate were higher due to an early dominance of dark energy, the cooling would have been more rapid, potentially freezing out nuclear reactions before they could proceed to completion. Conversely, a slower expansion rate would have allowed reactions to occur for a longer period, influencing the eventual abundance of elements. Dark energy's effects can be seen most clearly now, when its pushing force speeds up the split of galaxies, but they have been around since the beginning of the universe. Some models of the universe show that dark energy may have played a small but important role in how the universe moved during nucleosynthesis. In these models, dark energy changes how the universe has expanded over time, changing important factors, such as the ratio of baryons to photons and the general timing of the reaction freeze-out. This change could affect how common different light elements are, but normal Big Bang nucleosynthesis still fits with what we know about hydrogen and helium. Dark energy is a very important force in the universe that affects more than just nucleosynthesis. It's getting harder for galaxies and groups to stay close to each other as the universe stretches, because dark energy is making its effects stronger. Because of this growth, the forces that hold galaxies together become weaker over time. This makes the universe more and more separated. Even the gravitational pull of supermassive black holes and dark matter halos will not be able to stop the universe from expanding forever in a universe dominated by dark energy. This sets the stage for events like the Big Freeze, in which all cosmic activity stops as energy is spread out evenly. The impact of dark energy is also evident in the measurements of cosmological parameters. Observations of the cosmic microwave background, CMB, and large-scale galaxy surveys have been used to constrain the equation of state parameter, W, for dark energy, which relates its pressure to its energy density. A value of W close to 1 is consistent with a cosmological constant, implying that dark energy is a fixed property of space. However, even small deviations from this value could have significant implications for the long-term evolution of the universe. For example, if dark energy were to vary over time, it could alter the predicted timeline for the universe's expansion and impact the future of cosmic structures. Quantum effects at the birth of the universe. As the world was first being formed, the uncertainty principle was one of the most important quantum effects. This principle says that you can't measure two physical traits at the same time with arbitrary accuracy. This means that even in a vacuum, there are virtual particles popping in and out of existence all the time. In the early universe, when there was a lot of energy, these changes in the vacuum were much stronger. They not only caused small changes in the amount of energy in space, but they also caused the first bumps in the road that later turned into the web of galaxies and clusters in the universe through gravitational instability. The period of cosmic inflation, a rapid exponential expansion that is hypothesized to have occurred just after the Big Bang, is closely tied to these quantum phenomena. During inflation, the universe expanded by many orders of magnitude in an infinitesimal amount of time. Quantum fluctuations that were initially microscopic were stretched to astronomical scales as space itself expanded. These fluctuations became frozen in as perturbations in the density of the universe. When inflation ended, these seeded variations acted as the scaffolding for the formation of all subsequent cosmic structures. In this way, inflation not only resolves several classical puzzles, such as the horizon and flatness problems, but also provides a mechanism by which the inherently quantum nature of the early universe can have a lasting macroscopic impact. The interaction of quantum mechanics with gravity at the birth of the universe has inspired the quest of a theory of quantum gravity. Although it effectively explains gravity over long distances, classical general relativity ignores the behavior of spacetime at the lowest scales, where quantum events predominate. The search for quantum gravity seeks to unite these two frameworks into a single coherent theory capable of explaining events like the first singularity, the point at which conventional physics forecasts limitless density and curvature. Several techniques have been suggested to meet this difficulty, including loop quantum gravity and string theory. Though a comprehensive theory of quantum gravity is still difficult, insights from these disciplines imply that a state of limited, though quite high density, may replace the classical singularity, where quantum effects smell out the infinities. Tunneling is another fascinating quantum phenomena that has implications for the early cosmos. In classical physics, a particle must overcome a barrier to transition from one state to another. However, quantum tunneling enables particles to pass through barriers, even when they lack the energy to do so traditionally. In the early cosmos, quantum tunneling may have allowed for transitions between distinct vacuum states. This process might have caused a phase shift that significantly altered the basic forces and particle interactions, laying the groundwork for the cosmos we know today. The impact of quantum effects is not confined to the formation of structures alone. They also influence the evolution of the cosmic microwave background, CMB radiation. The slight temperature fluctuations observed in the CMB, variations of 1 part in 100,000, are the imprints of the primordial quantum fluctuations. By studying these anisotropies, scientists can infer not only the initial conditions of the universe, but also test the predictions of inflationary models and other theories that incorporate quantum mechanics. The singularity and the limits of classical physics. The singularity is a central idea in the Big Bang hypothesis that questions our current knowledge of physics. At this time, our standard physical laws disintegrate, as predicted by classical general relativity, which states that density and curvature would become limitless. It was previously believed that all energy and matter had been concentrated into one tiny, very dense point at the instant just before our universe came into being. Having said that, this infinite state isn't really a physical reality. Rather, it shows how far our ideas have come. Classical general relativity, formulated by Einstein, has been incredibly successful in describing the large-scale structure of the cosmos and the behavior of gravitational forces. Yet, when applied to the extreme conditions near a singularity, its predictions become nonsensical. The equations simply yield infinities where physical quantities, such as density and temperature, should be finite. These divergences signal that the theory is incomplete. It works remarkably well under most circumstances, but fails when pushed to the extremes of space-time curvature. The breakdown of classical physics at a singularity has long been viewed as a profound problem, indicating that a more comprehensive theory is needed to describe the earliest moments of the universe. The search for a theory of quantum gravity is a hopeful way to solve these problems. At the tiniest scales, where doubt and quantum fluctuations have the most impact, quantum physics describes how particles behave. General relativity gives us a geometric understanding of gravity. Scientists hope to build on this to make a theory that can explain things that happen in places where strong gravitational forces and quantum effects are important. Several theories, including string theory and loop quantum gravity, suggest that the classical singularity could be changed to a state with a very high density that has a limit. In these models, quantum effects smear out the singularity, getting rid of the confusing infinities and painting a clearer picture of how the universe came to be. Another approach to understanding singularities involves examining the nature of space-time itself. In classical physics, space-time is treated as a smooth continuum. However, many theoretical physicists suspect that at the Planck scale, around 10 to 35 10 minus 35 10 to 35 meters, spacetime might have a discrete or quantized structure. If spacetime is composed of tiny, indivisible units, then the idea of a continuous collapse into an infinitely dense point may be an oversimplification. Instead, the quantization of spacetime might impose a natural limit on how small regions can become, thus preventing the formation of an actual singularity. This concept is central to some versions of loop quantum gravity, where the fabric of spacetime is woven from finite loops, and the classical singularity is replaced by a bounce that could, in theory, lead to a new phase of cosmic expansion. Recent advances in high-energy astrophysics and gravitational wave astronomy have begun to provide indirect evidence that may eventually help resolve these theoretical challenges. For example, the observation of gravitational waves from black hole mergers gives us data on how extreme gravitational fields behave and evolve. These observations, when combined with improved numerical simulations, are gradually painting a clearer picture of what happens in regions where classical physics no longer applies. While we are still far from a complete theory of quantum gravity, these insights encourage scientists to refine our current models and explore new physics that might explain the nature of singularities. Inflation theory and its impact on early cosmology. The idea of inflation is one of the most important new ways we can think about how the world came to be. The idea of inflation was first put forward in the early 1980s. It says that a fraction of a second after the Big Bang, the universe went through a period of exponential growth, growing by at least 102610 circumflex, 1026 times in less than 1032 minus 32 10 to 32 seconds. This fast growth not only explains the cosmic microwave background, CMB's amazing uniformity, but it also solves some old puzzles that had been bothering cosmologists for a long time, like the horizon, flatness, and monopole problems. Most of the time, inflation is based on the idea that the universe was pushed along by a high-energy vacuum state called the inflaton. During inflation, the inflaton field's energy level stayed almost the same, which made space grow faster and faster. Any original irregularities were spread out by this uniform expansion. This successfully smoothed the fabric of space-time, creating the amazingly uniform and isotopic universe we see today. However, the quantum fluctuations that were already present in the inflaton field were not totally erased. Instead, they were blown up to cosmic levels. After a while, these boosted fluctuations became the building blocks for the universe's large-scale structure, which is what made galaxies and clusters appear all over the universe. Making the world almost flat is one of the most important things that inflation does. The standard view of cosmology says that the shape of the world depends on how dense the energy is in comparison to a certain density. It would be possible for the universe to quickly split into an open or closed shape if this critical mass didn't change. But when there is inflation, the density measure gets very close to 1 because of exponential growth. This smooths out any initial curves. The CMB readings, which show that the universe is flat in space and has a very small error range, are a lot like this finding. Inflation also provides a natural explanation for the observed absence of magnetic monopoles and other exotic relics predicted by grand unified theories, GUTS. In the extremely hot conditions of the early universe, these hypothetical particles should have been produced in abundance. However, the rapid expansion dilutes their density to such an extent that they become virtually undetectable in the present epoch. This dilution not only aligns with current observational evidence, but also alleviates potential conflicts between theoretical predictions and empirical data. The dynamics of inflation have deep implications for our understanding of cosmic time and the evolution of the universe. The transition from the inflationary phase to the radiation-dominated era, known as reheating, marks the moment when the inflaton field decays into standard model particles, repopulating the universe with matter and radiation. This process sets the initial conditions for Big Bang nucleosynthesis, influencing the abundances of light elements such as hydrogen, helium, and lithium. In this way, inflation not only explains the large-scale uniformity of the cosmos, but also plays a crucial role in determining its chemical composition. While inflation theory has had a lot of success, it does have some problems. One of the most important things to do is figure out exactly what the inflaton field is and what its potential is. This must be done in order to get the needed time of exponential growth. The inflationary paradigm also explains many things we see in the world very well, but it also makes us wonder what happened before inflation and how it fits into a bigger theory that ties together quantum physics and general relativity. New discoveries in observational cosmology, like taking very accurate readings of the CMB and doing large-scale studies of structure, have made the case for inflation stronger. These findings not only show that the universe is flat, but they also show minor patterns that are typical of an inflationary age, such as the nearly scale-invariant spectrum of primordial fluctuations. Next-generation satellites and ground-based telescopes are some of the projects that will be able to study inflation even more closely in the future. These missions may help us learn more about the energy scale of inflation and the physics of the inflaton. Advanced cosmological simulations. Advanced cosmological simulations have become indispensable tools for probing the mysteries of the early universe and understanding the complex processes that governed its evolution. By harnessing the immense computational power available today, scientists are able to recreate the conditions of the early universe in a digital environment, testing theoretical models and refining our predictions about cosmic evolution. These simulations integrate the fundamental equations of general relativity, fluid dynamics, and particle physics to generate detailed three-dimensional models that capture the non-linear interplay between gravity, radiation, and matter. Cosmological simulations have made one of their main successes their capacity to replicate the development and construction of major structures. Starting the simulations with small density fluctuations, thought to represent the remains of quantum fluctuations magnified during the inflationary period. Researchers may track the expansion of these disturbances across billions of years. Gravity magnifies these tiny fluctuations in the simulation, producing the cosmic web, a huge network of filaments, clusters, and voids reflecting the current galaxy distribution. By means of direct comparison between their models with astronomical surveys and CMB data, this virtual reconstruction of the cosmos helps scientists to validate the Big Bang hypothesis and the inflationary paradigm. Moreover, sophisticated simulations have shown the complex mechanisms of galaxy creation and development. They let scientists investigate how the interaction of dark matter, gas dynamics, and feedback from star formation and active galactic nuclei, AGN, forms galaxy assembly. Scientists may investigate the impact of many physical processes, such as cooling rates, star formation efficiency, and the influence of supernova explosions, on the resultant structure of galaxies by adjusting variables inside these models. These studies offer vital new perspectives on the mass distributions and observable variety of galaxy forms. Apart from simulating structure development, cosmological models are essential for comprehending the evolution of black holes and the earliest stars. High-resolution simulations show how population 3 stars, massive short-lived stars created from pure gas, emerged in the early universe by capturing the collapse of primordial gas clouds under the force of gravity. The enrichment of the interstellar medium with heavier elements by the radiation and supernova explosions from these stars was essential for the subsequent development of more complicated stars and planetary systems. Furthermore, models of black hole development and expansion via accretion and mergers have given insightful forecasts that are presently under testing using gravitational wave observatories such as LIGO and Virgo. The ability of these simulations to include and evaluate several cosmological theories is another crucial feature. Researchers can thus replicate situations like different levels of dark energy or changes to the rules of gravity. Understanding the quality of the mainstream cosmological model and investigating the possible consequences of novel physics depend on such comparison research. Analyzing how variations in basic characteristics influence the history of the universe helps scientists to better limit the theories explaining cosmic expansion, structure development, and matter and energy distribution. Technological improvements in numerical techniques and high-performance computers have resulted in simulations with unparalleled degrees of detail. Modern simulations use adaptive mesh refinement and advanced algorithms to achieve dynamic resolution, concentrating computing resources on regions of interest like galaxy clusters or black hole centers. This versatility allows researchers to represent both the universe's large-scale activity and the small-scale processes required for star and planet formation, all within a single simulation framework. High-precision measurements and their implications. High-precision measurements have transformed our knowledge of the early cosmos, providing a precise view of its formative processes. With cutting-edge technology and novel observational techniques, scientists can now monitor cosmic occurrences with unprecedented precision. These observations not only support our theoretical models, but also reveal minor abnormalities that call into question prevailing paradigms, resulting in the creation of new cosmological ideas and technologies. The cosmic microwave background, CMB radiation, is a key source of high-precision data. Satellites like COBE, WMAP, and Planck have mapped the CMB in remarkable precision, documenting temperature variations as small as 1 part in 100,000. These minute changes represent the traces of quantum fluctuations from the early cosmos, which were stretched to cosmic sizes by the inflation process. Cosmologists can derive essential characteristics, such as the universe's age, composition, and shape from these variations. The comprehensive angular power spectrum of the CMB, for example, gives information into the density of baryonic matter, dark matter, and dark energy, while also serving as a rigorous test for inflationary theories. In addition to the CMB, high-precision measurements extend to large-scale structure surveys. Advanced telescopes and dedicated surveys, such as the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, have charted the distribution of galaxies over vast cosmic distances. By measuring redshifts with exceptional accuracy, these surveys enable researchers to reconstruct the expansion history of the universe and test the predictions of the Big Bang model. The clustering of galaxies, as revealed by these surveys, offers clues about the initial conditions of the universe and the influence of dark matter on structure formation. These datasets, combined with CMB observations, create a comprehensive picture of cosmic evolution from the earliest times to the present day. Big Bang Nucleosynthesis, BBN, is another important field gaining from very accurate methods. Sophisticated spectroscopic techniques quantify observations of primordial light element abundances, including hydrogen, helium, and lithium. Testing the hypotheses of nucleosynthesis models depends on these observations, hence they are absolutely essential. Any differences between the expected and actual abundances suggest either novel physics or need changes to our present knowledge of the early cosmos. For example, the ongoing mismatch in lithium abundance, known as the lithium problem, has led scientists to rethink the basic mechanisms driving the initial few minutes following the Big Bang. Advancements in gravitational wave astronomy have opened a new high-precision window into cosmic events. Instruments like LIGO and Virgo detect the minute ripples in spacetime generated by black hole and neutron star mergers. The precise measurements of the waveforms from these events allow scientists to deduce properties such as the masses, spins, and distances of the merging objects. These observations not only test general relativity in the strong field regime, but also provide independent estimates of the Hubble constant, which measures the expansion rate of the universe. This dual role helps to cross-check and refine our cosmological models. The integration of data from multiple sources, CMB, galaxy surveys, nucleosynthesis, and gravitational waves, has led to a new era of multi-messenger astronomy. High-precision measurements across different wavelengths and messengers are increasingly used together to build a coherent picture of the universe's history. This interdisciplinary approach minimizes systematic uncertainties and maximizes the reliability of the conclusions drawn about the cosmos. Interdisciplinary approaches to early universe studies. Astronomical observations alone aren't enough to understand the early universe. We also need to combine what we know about astronomy, nuclear physics, particle physics, and even computer science. Combining experimental data with theory models and advanced simulations is how interdisciplinary methods help researchers solve hard problems, like the lithium difference. This joint structure not only helps us understand Big Bang nucleosynthesis better, but it also gives us new ways to look into the physical processes that shaped the universe when it was just starting out. In the field of nuclear astronomy, working together with people from different fields has been very important. Some scientists in this field use ideas from both nuclear physics and observational astronomy to try to figure out what happened in the first few minutes after the Big Bang. These models show how hydrogen, helium, and small amounts of lithium, which are light elements, were made at very high temperatures and pressures. Scientists can check if the Big Bang model is correct by comparing the expected abundances from these models with the ratios of elements found in the oldest stars and gas clouds. When differences show up, like the unexpectedly high amounts of lithium, it makes both nuclear scientists and cosmologists rethink the reaction rates and cross-sections that were thought to be normal in the early universe. The work that astrophysicists and particle scientists do together is also very important. Particle physics gives us the tools to study how basic particles behave and the forces that act on them, especially at very high energies, like those found in the early universe. Particle accelerators like the Large Hadron Collider are used to do experiments that mimic conditions that were present right after the Big Bang. These experiments help us understand how matter and energy interacted at that time. These studies have also helped us learn more about processes like baryogenesis, which is the creation of matter over antimatter, and has a direct effect on nucleosynthesis. These kinds of discoveries are very helpful in solving the lithium problem, because even small changes in how particles interact can have big effects on how elements form. Computational science also plays a vital role in this interdisciplinary effort. High-performance simulations are used to model the complex dynamics of the early universe, from the behavior of the inflaton field during cosmic inflation to the detailed chain of nuclear reactions during nucleosynthesis. These simulations require expertise in numerical methods, statistical analysis, and computer science, creating a bridge between theoretical predictions and observable phenomena. By incorporating data from a variety of sources, such as spectral observations, CMB measurements, and particle accelerator experiments, researchers can iteratively refine their models. This iterative process not only helps in understanding the standard Big Bang model, but also in testing alternative theories that might explain anomalies like the lithium discrepancy. Putting together observational data with theory models has also led to the creation of new ways to analyze data. For example, machine learning techniques are being used more and more to sort through huge amounts of data about the stars and find small trends that would be missed otherwise. Then, these patterns can be compared with what nucleosynthesis models say will happen. This gives us a better idea of how different things, like changes in the speed at which the universe is expanding, or the amount of energy in the early universe, affect the amounts of different elements. These kinds of methods that combine different fields are necessary to learn more about the early world. Interdisciplinary approaches also extend to collaborative efforts across international research communities. Large-scale projects like the Planck satellite mission and the Sloan Digital Sky Survey bring together experts from multiple fields and institutions around the world. This pooling of resources and expertise accelerates progress by enabling the cross-validation of results and fostering an environment where ideas are challenged and refined from multiple perspectives. It also ensures that the latest advancements in technology and methodology are rapidly incorporated into our models of the early universe. Alternative theories to the Big Bang. While the Big Bang model remains the prevailing theory of cosmic origins, a number of alternative theories have been proposed over the decades to explain the universe's inception and evolution. These alternative models aim to address some of the conceptual and observational challenges that the standard Big Bang paradigm faces, such as the singularity problem and certain elemental discrepancies. By exploring these models, scientists seek not only to refine our understanding of the early universe, but also to uncover deeper insights into the fundamental nature of space, time, and matter. The steady-state theory was one of the first alternatives. It said that the world has always been in a steady state without a clear starting. In this model, new matter is always being made to fill in the gaps left by the universe's growth. This keeps the density of the universe stable over time. The steady-state theory was popular until the cosmic microwave background, CMB, and the known evolution of galaxies came along. However, it was very important in starting arguments about the beginnings of the universe and what an eternal universe is like. The cyclic or oscillatory universe idea is another strong option. For the circular model, the universe doesn't start with a single explosion. Instead, it goes through endless rounds of expanding and contracting. This idea says that the universe might grow to its biggest size, then shrink in a big crunch, and then grow again in a new phase of growth, which is sometimes called the Big Bounce. Supporters say that these cycles could automatically change the way the world works, which could help with problems like the buildup of entropy over time. Over the years, this model has been improved with new ideas like the ekpyrotic universe, which says that our universe may have formed when higher dimensional branes crashed into each other. These brain impact models use string theory and give a new way to look at how the universe could be both circular and have come into being from multiple universes. Bouncing cosmologies have garnered significant interest because they offer solutions to the singularity problem that plagues the standard Big Bang model. In these models, the universe does not begin from an infinitely dense point. Rather, the collapse of a previous universe is halted by quantum gravitational effects, causing a rebound that initiates a new phase of expansion. The advantage of a bounce is that it removes the need for a singularity, a point where the laws of physics as we know them cease to operate, thus providing a more coherent framework that might integrate with quantum mechanics. Researchers working in loop quantum gravity, for instance, have developed models in which spacetime is discrete, and the classical singularity is replaced by a quantum bounce. These models suggest that the universe could undergo a smooth transition from contraction to expansion, with quantum effects preventing the formation of infinite density. There are more different theories than just the idea of a cyclical world. Sir Roger Penrose came up with the idea of conformal cyclic cosmology, CCC, which says that the Big Bang of one eon is the far future of another. In this view, the shape of the universe and the way time works are rethought in a way that allows the current universe's endless growth to change into a new, less chaotic state that starts a new Big Bang. Even though the CC is based on a lot of speculation and is still being talked about, it gives an interesting answer to the problem of cosmic singularities and makes forecasts that can be tested by looking at patterns in the CMB. Changes to the gravitational structure are part of another group of alternative ideas. Some experts think that we might need to make changes to general relativity or come up with completely new theories of gravity in order to fully understand how the universe came to be. It's possible that these changes could have affected the early universe's processes, changing the conditions for nucleosynthesis and even the amounts of elements that have been seen. For instance, theories that add extra dimensions or use modified gravity models like FR gravity can make different predictions about how the universe grew and how structure was formed. This means that they can explain some problems, like the lithium problem, in different ways. Each of these alternative theories shares a common goal: to provide a more complete, self-consistent picture of the universe's origins that addresses the shortcomings of the standard Big Bang model. They challenge us to rethink fundamental assumptions about the nature of time, space, and the very beginning of existence. Although many of these models remain speculative and require further empirical support, they play a vital role in driving the field forward by inspiring new observations and experiments that test the limits of our current theories. Re-evaluating fundamental constants in the early universe. The early universe was governed by a set of physical constants that set the stage for all subsequent cosmic evolution. Constants such as the gravitational constant, g, the speed of light, c, and the fine structure constant, alpha, determined the behavior of matter and energy and influence processes ranging from nucleosynthesis to galaxy formation. However, recent high-precision measurements and theoretical developments have raised the possibility that these constants might not have been truly constant in the earliest moments of the universe. This section examines how slight variations in fundamental constants could have impacted nucleosynthesis and altered the predicted abundances of light elements, potentially offering a fresh perspective on discrepancies like the lithium problem. Along with alpha, the gravitational constant, g, also has a direct effect on how fast the world is expanding. If g had been higher or lower in the early universe, it would have changed the rate of expansion, which in turn changed the temperature and density conditions where nuclear processes took place. These changes could throw off the balance between different nuclear reaction paths, which would have an effect on the total amount of elements made during nucleosynthesis. For example, a slightly higher G could cause the initial plasma to collapse and cool down more quickly, which would cut down on the time for nuclear reactions and could lower the total production of some isotopes. The baryon to photon ratio is another critical parameter that has been scrutinized. This ratio influences the density of matter relative to radiation, and is a key determinant of how quickly the universe cools after the Big Bang. Any deviation from the currently accepted value would change the reaction rates during nucleosynthesis. Observational data from the CMB provide a precise measurement of this ratio, yet theoretical models continue to explore whether a dynamic baryon to photon ratio in the very early universe might reconcile some of the observed discrepancies in elemental abundances. New discoveries in observational astronomy and particle physics have led to new tests that try to find any changes in these constants. Using atomic clocks and laser interferometry in the lab has pushed the edges of what we can do to measure changes in the fine structure constant over time. Theoretically, models that include scalar fields that interact with matter, like the inflaton field in inflationary theory, suggest that what we think of as a constant may actually be the result of a changing process that settled into a stable number. These models suggest that when the universe was young and full of energy, fundamental constants may have changed slowly over time, with the numbers we measure now being the final steady state. Philosophical implications of a controversial Big Bang model. The ongoing argument about the lithium difference and other elemental oddities in the Big Bang model makes us think about different philosophical questions about what science truth is and how we know about the beginning of the universe. At its core, this debate questions the idea that the models we use now give us a full and unchangeable account of how the world came to be. Instead, it says that our current view of the universe may be less solid and more open to change than we thought. A case in point is lithium abundances. When predictions and data don't match up, it makes scientists and thinkers rethink the basics of how we understand the world. One important philosophical consequence revolves around the boundaries of empirical knowledge. Supported by a lot of observational data like the cosmic microwave background and hydrogen and helium abundances, the Big Bang hypothesis has long been seen as one of the foundations of contemporary cosmology. But the ongoing disparity with lithium calls into doubt the idea that one simple, elegant theory can explain all facets of the history of the cosmos. This promotes a more modest perspective of scientific research in which hypotheses are considered as developing approximations that need constant improvement in front of fresh facts. This makes the lithium issue a metaphor for the general ambiguity of our attempts to comprehend events under harsh conditions billions of years ago. The debate also brings up philosophical questions regarding the function of basic constants informing reality. Our knowledge of the universe may be rather dependent on parameters that might not be as constant as presumed if little differences in constants like the fine structure constant or the gravitational constant cause considerable changes in the expected constituent abundances. This notion begs issues regarding the nature of physical laws. Are they emergent features that may have developed together with the world itself, or are they immutable rules guiding a fixed reality? Such thoughts help us to consider the dynamic interaction between the cosmic evolutionary processes and the natural constants. The lithium difference challenges us to review the link between theoretical predictions and empirical data. It underlines the need of keeping an open, critical attitude in science and questions the idea of an ultimate correct hypothesis. In the field of philosophy of science, this problem emphasizes the underdetermination theory, where several theories may explain the same set of observations, and reminds us that our present models could be only one of many reasonable explanations of cosmic history. These arguments have more general metaphysical ramifications for our position in the cosmos. Should the conditions of the early universe and the values of its basic constants differ from what is now believed, then the formation of life and awareness may be understood as dependent on a careful equilibrium of cosmic events. This viewpoint not only enhances our scientific story, but also gives it a wonder and connection that goes beyond simple material explanations. Technological advances driving cosmology forward. The building of telescopes in space was one of the most important technical advances in the field of cosmology. Instruments like the Hubble Space Telescope, the Planck satellite, And most recently, the James Webb Space Telescope, JWST, have made it possible to see the universe like never before. Because these telescopes are able to work above Earth's atmosphere, they can take pictures and spectra with very little interference. This lets them see very clearly information about faraway galaxies, areas where stars are being formed, and the cosmic microwave background, CMB. For example, Planck's detailed mapping of the CMB has helped scientists carefully measure changes in temperature and polarization patterns, which in turn help us figure out how the universe began and how it has changed over time. Advances in ground-based astronomy have also played a critical role. Next-generation telescopes like the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, are set to further revolutionize our understanding of cosmic structures. With their enormous light-collecting areas and state-of-the-art adaptive optics systems, these telescopes will resolve fine details in distant galaxies, track the motions of stars in unprecedented detail, and even study the environments of supermassive black holes. Such observations are essential for testing the predictions of the Big Bang model and for refining our knowledge of dark matter, dark energy, and the processes of galaxy formation. Along with images and spectroscopy, new observing methods have come up that give us more tools for studying the universe. Space telescopes like LIGO and Virgo have made gravitational wave astronomy possible. They let us hear the universe by picking up the ripples in space-time caused by supermassive events like black holes merging and neutron stars crashing into each other. These findings add to what we know about electromagnetic waves and have already proven important parts of general relativity in very harsh circumstances. The realm of computational astrophysics has also experienced transformative advances. High-performance computing enables researchers to run complex simulations that model the evolution of the universe from its earliest moments to the formation of large-scale structures. These simulations incorporate the fundamental equations of physics, ranging from general relativity to quantum mechanics, and allow scientists to test various theoretical scenarios. Adaptive mesh refinement techniques and sophisticated numerical algorithms ensure that these simulations capture both the vast cosmic scales and the fine details of processes such as nucleosynthesis and star formation. The integration of machine learning and artificial intelligence into data analysis is accelerating discovery in cosmology. With the explosion of data from new observatories, AI tools are now essential for sorting through terabytes of information to identify subtle patterns and anomalies that might point to new physics. These techniques help to cross-match observational data with theoretical models, leading to more robust and precise conclusions about the nature and history of the universe. Future observational prospects in cosmology. Making the next wave of space telescopes is one of the most exciting things that could happen. Missions like the Nancy Grace Roman Space Telescope and possible replacements for the James Webb Space Telescope, JWST, should make it easier to see things in a wider range of colors, from visible light to near-infrared light. Astronomers will be able to see the oldest galaxies, study how stars form and change over time in ways that have never been done before, and even look more closely into the reionization age. These telescopes will help us figure out how the early universe worked by picking up the faint light of the first bright objects. This will help us figure out when cosmic structures formed and what physical processes controlled them. Ground-based observatories will also play a crucial role in the coming years. The Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, are set to revolutionize optical and near-infrared astronomy with their enormous apertures and cutting-edge adaptive optics systems. These facilities will provide high-resolution imaging of distant galaxies, allowing us to map the distribution of dark matter through gravitational lensing and to study the dynamics of galaxy clusters in detail. In addition, radio observatories like the Square Kilometre Array, SKA, will offer new insights into the distribution of neutral hydrogen and the large-scale structure of the universe, complementing the data obtained at other wavelengths. A major leap in observational cosmology is anticipated from the burgeoning field of gravitational wave astronomy. With the success of LIGO and Virgo, future missions such as the Laser Interferometer Space Antenna, LISA, and the planned Einstein Telescope will extend the range of detectable gravitational wave frequencies. These space-based observatories will be sensitive to waves emitted by supermassive black hole mergers and other low-frequency events that are currently beyond our reach. Gravitational waves provide a unique probe of the universe's most violent phenomena, and their detection will help resolve questions about the formation of black holes, the evolution of galaxies, and even the behavior of gravity under extreme conditions. As data processing and analysis get better, we should be able to observe things even more clearly. More and more, methods like machine learning and artificial intelligence are being used in the processing processes for high-resolution imaging and large-scale surveys. Astronomers will be able to sort through huge amounts of data with these tools to find small signs and trends that could point to new physics or strange things happening in the structure of the universe. Better ways to use computers will also make it possible to run more accurate simulations of how the universe has changed over time. This will make it easier to compare theory forecasts with data from observations. Implications of the lithium problem for cosmological model. The question of making elements in the first few minutes after the Big Bang is at the heart of the lithium problem. Standard BBN theory says that the nuclear processes that happened at very high temperatures and densities should have made light elements in the right amounts. The amounts of hydrogen and helium that have been found match these estimates amazingly well. Lithium, on the other hand, is a strange case. The models forecast about 3 times more lithium-7 than what scientists find in the oldest stars. This discrepancy has stayed the same despite many improvements to both observations and theories. This mismatch has significant implications, including the possibility that our knowledge of nuclear reaction rates in the early cosmos is insufficient or perhaps erroneous. Small changes to the reaction cross-sections or speeds of these reactions might have a major impact on the expected lithium yields. This potential has rekindled interest in both experimental nuclear physics and theoretical modeling, with researchers employing improved simulations and laboratory data to re-evaluate the nuclear processes that lead to nucleosynthesis. If future studies show that these rates deviate from present estimates, the conventional BBN calculations may need to be revised, affecting not just the anticipated abundances of lithium, but also of other light elements. The role of basic constants in the early world is another area that has a big effect. Some experts think that small changes in constants, like the fine structure constant or the neutron lifetime, might have caused nucleosynthesis to happen differently. Even small changes in these numbers could have an effect on how well nuclear reactions work, which would change the predicted lithium rates. If proof of changeable constants comes to light, it would not only help solve the lithium problem, but it would also change the way we think about how physical laws worked in the early world. These results could mean that things we think of as constant now were actually changing over time. This would lead to a more complex and adaptable model for how the universe evolved. The lithium problem also touches on the influence of dark matter and dark energy during nucleosynthesis. Although these components are not directly involved in the nuclear reactions that form light elements, they affect the overall expansion rate of the universe. Dark energy, in particular, drives the accelerated expansion that determines the time-temperature relationship during BBN. A faster or slower expansion rate can change the window during which nuclear reactions are efficient, thereby influencing the final abundances of elements. If alternative models of dark energy or dark matter lead to a different expansion history, this could provide a natural explanation for the lower than expected lithium levels. Hence, resolving the lithium problem might necessitate a broader revision of how these elusive components interact with standard matter in the early universe. Also, the lithium difference might make cosmologists think about the chance of new physics that are not part of the standard model. Several ideas have been put forward as possible answers to the lithium problem. These include the breakdown of massive particles or changes in the features of neutrinos. These new physics situations could change the thermodynamic conditions or add more reaction paths during BBN, which would lower the amount of lithium that is made. If these processes are proven by separate experiments or observations, it would be a big change in both cosmology and particle physics. It would open up new study areas and might even lead to a new cosmological model that fits observational data better. When you think about the bigger story of the universe, the effects go even further. The lithium problem is a stark warning that we still don't fully understand how the world began and how it has changed over time. The difference makes us rethink the assumptions that are models of how the universe evolved, because it challenges the normal Big Bang model on such a basic level. This process of re-examination is important for scientific growth because it leads to the creation of more accurate models that include more details. This could be through updated nuclear physics, dynamic basic constants, or completely new physics that goes beyond the standard model. Impact of revised models on our cosmic narrative. One big effect is that it could change how we think about the universe's temperature past in a big way. Traditional models of the Big Bang have long suggested that the universe cooled evenly from a very hot and dense state, creating known amounts of light elements. But if new models show that important factors like reaction rates or fundamental constants were different in the early universe, then the cooling curve and the order of events during nucleosynthesis would need to be rethought. This new way of thinking might show a more complicated interaction of forces in the early universe, which could change how long important events like recombination and the creation of the first atoms lasted. As a result, we might have to rethink what we know about the matter-antimatter imbalance. The standard Big Bang model says that certain amounts of light elements should have been present, but the lithium difference suggests that some processes are not fully explained. These processes could involve the loss of exotic particles or changes in neutrino properties. If we look at these models again, we might learn more about why matter, not antimatter, rules the world we can see. This could change the story of one of cosmology's oldest mysteries, the unbalance that made room for stars, galaxies, and eventually life. And once the lithium problem is solved, we might have to rethink what role dark matter and dark energy played in the early universe. New models could show that dark matter wasn't as still during nucleosynthesis as was thought before, or that dark energy had a slightly different effect on the rate of growth. Such changes would affect how we understand how cosmic structures are made. In the early universe, if dark matter played a more active role in cooling it down, it might explain strange differences, not only in the amounts of different elements, but also in how galaxies were spread out on large scales. Because of this, the new story would show these forces as involved in the formation and growth of cosmic structures, not just as background effects. It changes more than just the story we tell about the universe's distant past. It also changes how we think about the present and the future. A new model that better matches theory expectations with observational data could change how we think about how the universe evolved later on, from how the first stars formed to what happened to galaxies in the end. If the early universe was more complicated than the standard model says, then the steps that galaxies take to change over time, stars form, and even planetary systems form might be different. This big picture view disagrees with the idea that the history of the universe is a straight line that doesn't change. Instead, it suggests that the story is dynamic and is still unfolding. Figuring out the lithium gap could lead to combining quantum mechanics and general relativity, which is an important goal in theoretical physics that has been pushed back for a long time. If the change that adds quantum corrections to nucleosynthesis models works, it could connect the microcosm to the macrocosm and give us clues about how physical rules are connected. In turn, this could change everything we know about how basic forces work together and how the world has changed over billions of years. Revised models have changed the way we think about the world as a whole, which makes us feel humble and curious about our place in it. As we make changes to our models to fit new information, we are told that science is a conversation that is always going on, a story that is improved as our observational methods and theoretical understanding grow. This changing process not only helps us learn more about the universe, but it also encourages people to come after us to question, explore, and change the story of our universe. Connections between cosmic origins and modern astrophysics. The way that the elements that were formed in the first few minutes after the Big Bang affect later stages of cosmic development is one of the main links between the history of the universe and current astrophysics. The expected amounts of hydrogen, helium, and lithium are not only a strong test of models of nucleosynthesis in the Big Bang, but they are also the building blocks for all processes that happen in stars afterward. Stars are the cosmic engines that make chemical enrichment possible. They are born from clouds of gas that are mostly hydrogen and helium. The early conditions of the universe set the stage for the creation of galaxies and stars. These conditions have had a direct impact on the development of cosmic structures over billions of years. Modern astrophysics also builds on the insights gleaned from the cosmic microwave background, CMB, which offers a snapshot of the universe at the moment of recombination. The minute temperature fluctuations observed in the CMB reveal information about the density variations that later evolved into galaxies and clusters. This early imprint allows astrophysicists to trace the evolution of large-scale structures and refine simulations of galaxy formation. Techniques developed to analyze the CMB have been adapted and expanded in modern observational astronomy, linking the earliest moments of the universe to the complex systems we study today. The ongoing quest to understand dark matter and dark energy is deeply rooted in the context of cosmic origins. The relative abundances of light elements, as well as the detailed measurements of the CMB, have provided stringent constraints on the amount of baryonic matter in the universe. Yet, we now know that this ordinary matter constitutes only a small fraction of the total mass-energy content of the cosmos. The remaining components, dark matter and dark energy, play a crucial role in shaping the universe's expansion and the formation of cosmic structures. Modern astrophysics leverages these early universe constraints to develop models that explain the rotational dynamics of galaxies, gravitational lensing phenomena, and the accelerating expansion observed in distant supernovae. These connections illustrate how foundational aspects of the Big Bang influence the behavior and evolution of the cosmos at all scales. The feedback processes between black holes and galaxies also find their roots in the early universe. The formation and evolution of supermassive black holes are linked to the processes that govern the primordial gas clouds in the first galaxies. Observations of active galactic nuclei, AGN, and the correlations between black hole masses and galaxy properties, such as the M-sigma relation, underscore the long-lasting impact of early cosmic conditions on the structure of galaxies. This intricate interplay between central black holes and their host galaxies, observed today, can be traced back to the initial density fluctuations and elemental abundances produced during the Big Bang. A busy area of research that connects cosmology and astronomy is the study of how cosmic structure has changed over time, from the birth of the first stars to the creation of galaxy clusters. As computer models of the universe get more complex, they include both the conditions that existed before the Big Bang and the astronomical processes that happen afterward and cause structures to form. These simulations not only prove that our theoretical models are correct, but they also help us guess what will be seen in the future. This brings the study of how the universe began even more closely together with current astrophysical research. The role of Big Bang cosmology in the modern scientific landscape. In the modern scientific landscape, the Big Bang theory has provided the foundation for explaining a multitude of observations that were once considered mysterious. For example, the discovery of the cosmic microwave background, CMB radiation, a relic glow from the early universe, has offered compelling evidence that the universe began in a hot, dense state. Detailed studies of the CMB not only reinforce the Big Bang model, but also allow scientists to extract precise information about the universe's composition, such as the relative amounts of hydrogen, helium, and other light elements. This has led to significant advances in our understanding of nucleosynthesis, the process that created the first elements, which in turn set the stage for the formation of stars and galaxies. The Big Bang model has also been very helpful in studying dark matter and dark energy, which are two of the biggest puzzles in modern physics. Observations of gravity lensing, star spin curves, and the universe's speeding expansion are all explained in terms of the Big Bang. These discoveries have led to the creation of new theory models and research methods that aim to reveal the nature of these mysterious parts. So, the Big Bang theory not only explains how the universe started, but it also changes the way we think about what will happen to it in the future. The influence of the Big Bang extends to the realm of particle physics as well. The theory provides the backdrop for the standard model of particle physics, linking the evolution of the universe to the behavior of fundamental particles and forces. Experiments conducted in particle accelerators like the Large Hadron Collider, LHC, often recreate conditions similar to those just after the Big Bang, allowing scientists to probe the properties of matter at its most basic level. These experiments have led to discoveries such as the Higgs boson, deepening our understanding of how particles acquire mass and further solidifying the Big Bang's role as the progenitor of cosmic structure. The Big Bang model has an effect on more than just science. It also has an effect on psychological and cultural debates about our place in the universe. It gives us a story that connects us to the beginning of the world and makes us think about the nature of life and the chance of a cosmic destiny. As a way to get people interested in science and help them understand the wonders of the world better, the Big Bang is often used in school settings. Criticisms and controversies surrounding the Big Bang model. The quantity of light elements created during Big Bang nucleosynthesis is another topic of ongoing debate. There is a big difference between what the model says about lithium and what it says about hydrogen and helium. It is thought that there will be 3 times as much lithium-7 as has been seen in the oldest metal-poor stars. Cosmologists and nuclear scientists have had a lot to say about this lithium problem. Some say that unknown physical processes may have used up lithium over the course of cosmic time, while others say that our ideas about the nuclear reactions that happened in the first few minutes after the Big Bang may need to be rethought. This difference calls into question the model's general ability to predict, and it has led to a lot of theory and experimental work trying to figure it out. The Big Bang model also faces scrutiny over its assumptions regarding the homogeneity and isotropy of the universe. The cosmological principle, the idea that the universe is the same in all directions on large scales, underpins the Big Bang model. However, detailed observations of the cosmic microwave background, CMB, have revealed tiny anisotropies, or temperature fluctuations, which are crucial for the formation of structure in the universe. While these fluctuations are generally well explained by inflationary theory, some critics argue that certain anomalies, such as the so-called axis of evil or unusual alignments in the CMB, might hint at new physics beyond the standard model, or even suggest that our observations are being skewed by unaccounted systematic errors. There is also disagreement about dark matter and dark energy, 2 important parts of the Big Bang model that are still mostly unknown. Even though the model successfully uses dark matter to explain how galaxies grow and how large-scale structures work, no one knows what dark matter is. In the same way, dark energy is used to explain why the expansion of the universe is speeding up, but its qualities are only hinted at. Some people say that the model isn't very solid because it depends on invisible parts that make up about 95% of the universe's energy mass. The Big Bang model can still be changed until dark matter and dark energy are directly found or better understood. Other theories even question whether these parts are necessary at all. There is also still some disagreement about the flatness and boundary problems, which are past issues that led to the creation of inflationary theory. Most people agree that inflation, the fast growth of the world in its early stages, is the answer to these problems. Still, inflation itself brings up new questions, like how to fine-tune the potential for inflation and what multiverse effects endless inflation scenarios have. Some critics say that inflation may solve some problems, but it may also make things more complicated by adding more theoretical ideas that haven't been tested in the real world yet. The lithium problem, in the context of overall cosmic evolution. There is a big problem with lithium that has to do with how nuclear physics and astronomy work together. The factors present during nucleosynthesis, such as temperature, density, and the rate of growth of the universe, have a big impact on how lithium is made in the early universe. Different lithium yields could be caused by small changes in these factors. This suggests that our current models may be missing important information about the microphysics of the early universe. For example, the expected abundance might become more in line with what we see if the reaction rates for making or breaking down lithium were a little different from what our lab readings show. Instead, if an unusual process, possibly involving particles outside of the standard model, changed the paths of nuclear reactions during nucleosynthesis, it could naturally lower the output of lithium. The lithium discrepancy does not exist in isolation. It is intrinsically linked to the overall evolution of the universe. The primordial abundances of light elements serve as critical probes of the conditions prevailing in the first moments after the Big Bang. They set the initial chemical composition from which all subsequent cosmic structures, from stars and galaxies to planets and ultimately life, emerged. In this context, any revision to our understanding of nucleosynthesis has far-reaching consequences. A corrected lithium yield would not only resolve a major inconsistency in our cosmic inventory, but could also require us to revisit our models of cosmic expansion and the thermal history of the universe. The rates at which the universe cooled, the duration of the nucleosynthesis epoch, and the subsequent formation of the first atoms all depend on these early reactions. Therefore, reconciling the lithium problem might lead to a more refined timeline of cosmic evolution that could impact our interpretation of later phenomena, such as galaxy formation and the reionization era. Cosmologists are also looking into the idea that the early universe may have been affected by things we haven't fully accounted for in our models because of the lithium problem. It's possible that dark matter and dark energy, which make up most of the universe's energy, had a more active part in nucleosynthesis than was thought before. Even though dark matter doesn't directly take part in nuclear processes, its gravitational pull may have had a small but noticeable effect on the universe's density and rate of growth, which could have had an impact on how well lithium is made. In the same way, changes in the properties of dark energy during the nucleosynthesis stage could have affected how fast the universe cooled down, which could have affected how much time was available for nuclear processes to happen. These points of view open up interesting options for new physics that could help connect theory and data. The lithium problem has also led to a more in-depth look into how reliable and useful optical readings are. The amount of lithium that has been found is based on studying spectral lines in old, metal-poor stars, which are thought to have kept the chemical signature from the beginning of time. But there are some unknowns about star atmospheres, diffusion processes, and other astronomical effects that could cause lithium levels to be consistently underestimated. Because of this, some experts say that the perceived difference might be partly due to the limitations of the methods we use to observe rather than a basic flaw in the Big Bang model. So, making spectroscopic data more accurate and coming up with new ways to look into the chemical makeup of old stars could help us understand this issue much better. Getting rid of the lithium problem will have effects that go far beyond nucleosynthesis. A good resolution would make the Big Bang model even stronger, which would help us learn more about the early world. On the other hand, if the difference stays even after taking into account possible theory and observational doubts, it could mean that our understanding of the universe needs to be completely rethought. A revision like this could include new physics, like basic factors that change over time, the presence of new particles, or different ways for elements to form. Comparative analysis of other elemental discrepancies. A significant example is the abundance of heavy metals such as gold, platinum, and uranium in some star populations. Traditional nucleosynthesis theories ascribe these elements' creation mostly to fast neutron capture processes, R processes, that occur during explosive events like supernovae or neutron star mergers. However, certain measurements indicate that the abundance of these elements in specific stars or galaxies exceeds theoretical estimates. This abundance compels astrophysicists to reconsider the habitats and conditions under which the R process functions. It raises concerns regarding the efficiency of heavy element synthesis, and if other or alternative astrophysical locations may contribute to the increased yields. Similarly, discrepancies have been reported in the abundances of beryllium and boron. While these light elements are not produced in significant amounts during standard Big Bang nucleosynthesis, they are created through spallation processes, where cosmic rays collide with heavier nuclei. The observed levels of beryllium and boron in some halo stars sometimes do not align perfectly with the predictions based on cosmic ray flux models and interstellar medium composition. This mismatch forces researchers to scrutinize the cosmic ray production, propagation, and interaction models, potentially pointing to gaps in our understanding of particle acceleration in the early galaxy. The issue with helium isotopes is likewise an intriguing instance. While helium-4 is one of the most reliable predictions of Big Bang nucleosynthesis, slight variations in the ratios of helium-3 to helium-4 have been seen. Though these variations are small in comparison to the lithium issue, they provide a sensitive test of the physics of the early cosmos. Small changes in reaction rates, the expansion rate of the cosmos, or the neutrino sector might cause differences in these ratios. Careful observations of helium isotopic ratios in low metallicity settings are still required to evaluate the Big Bang model's correctness and find any necessary adjustments. Examining these various elemental discrepancies collectively reveals a pattern. The early universe's nucleosynthesis appears to be more complex than the standard model suggests. The systematic over- or underproduction of certain elements may indicate that our current reaction networks and assumptions about the physical conditions during nucleosynthesis are incomplete. For instance, if multiple elements show deviations that point in the same direction, such as an overproduction of some heavy elements coupled with an underproduction of lithium, this could imply that additional physical processes or unknown particles were influencing nuclear reactions in the first few minutes after the Big Bang. The nuclear reactions that form lithium are part of a larger network that also affects the synthesis of other light elements. A revision in one reaction rate could have cascading effects on the predicted abundances of multiple elements. This interdependency emphasizes the need for a comprehensive re-examination of the nucleosynthesis network, rather than treating the lithium problem in isolation. Different theories have been put forward to explain these differences. Some experts want models that include differences in the early universe, where differences in density and temperature could cause nucleosynthesis to happen in different places. In these situations, the mean abundances found in the world right now might not match the statements made by homogeneous theory. Others think that physics outside of the standard model, like the decay of exotic particles or changes in basic constants, might be able to fix the expected elemental yields. Theoretical and observational challenges for the future. Observationally, it can be hard to get good data from old metal-poor stars that are used to estimate the amounts of elements in the beginning of time. A lot of the time, these stars aren't very bright, and their atmospheres can be changed over time by complicated internal processes like convection and mixing. So, it's not easy to separate the chemical fingerprints of the beginning from the effects of later development. Improvements in high-resolution spectroscopy and the creation of three-dimensional models of stellar atmospheres are necessary to lower the regular flaws in these measures, but they need a lot of computing power and complex analysis methods. The interaction of cosmic factors influencing the universe's expansion pace and the circumstances under which nucleosynthesis took place presents even another major challenge. Including contributions from dark matter and dark energy, the expansion rate throughout the nucleosynthesis period is sensitive to the total energy density. Any variations in the early expansion history may significantly affect the timing and efficiency of nuclear reactions, therefore changing the expected abundances. Derived from measurements of the cosmic microwave background and large-scale structure, current observational limits on these parameters are increasing. Tiny deviations may still evade detection, therefore complicating attempts to fine-tune nucleosynthesis models. Adding physics beyond the standard model to our understanding of the early world is still hard from a theoretical point of view. Several ideas suggest that the disintegration of exotic particles or minor alterations in fundamental constants may have impacted nucleosynthesis. However, proving these theories empirically is exceedingly challenging because to the energy scales required, which are frequently considerably above the capabilities of modern particle accelerators. These speculative theories, although interesting, add levels of complexity to an already complicated theoretical framework and need new physics that have yet to be explicitly seen. Future observational facilities and advances in experimental technology promise to help overcome some of these challenges. Upcoming missions with next-generation telescopes and space-based observatories are expected to deliver even more precise measurements of elemental abundances and cosmological parameters. In parallel, breakthroughs in nuclear physics experiments, such as improved particle accelerators and innovative techniques for simulating early universe conditions, could provide critical data to refine reaction rates further. Moreover, the integration of machine learning algorithms and advanced numerical simulations into the analysis of astrophysical data offers the potential to uncover subtle patterns and correlations that have so far remained hidden. While no model can perfectly capture the intricacies of our cosmic origins, our deep dive into the lithium problem reveals just how complex and dynamic the universe truly is. The challenges and breakthroughs we've explored today force us to re-evaluate the very foundation of the Big Bang theory and push the boundaries of our understanding of early cosmic nucleosynthesis. Each observation, experiment, and simulation brings us one step closer to unraveling the colossal puzzle of how the universe came to be. How does grappling with such a monumental error in our cosmic blueprint make you feel? Leave your thoughts in the comments below, and if this voyage into the origins of the cosmos sparked your curiosity, please like this video and subscribe to our channel for more explorations into the mysteries of the universe. Thanks for watching.